Hi everybody, it's Camille. I want to talk to you today about Starling forces, also known as oncotic and hydrostatic pressure in the capillaries. So before we start, I want to clear up one misconception that I run across often. What we're really talking about today is how fluid moves in and out of the capillaries. And as part of that discussion, you'll often hear about the interstitial space and the interstitial fluid. And what's not shown here in this diagram are cells, right? So you have cells outside of the capillary, and then you have this interstitial space. And you can see they've drawn it here almost like an ocean, like it's this sort of liquid ocean-like substance. And it turns out that's not really what it is at all. The interstitial space is primarily held up by the skeleton of collagen fibers. Okay, so we've got the skeleton of collagen fibers, and then this mesh of proteoglycans, which is just a combination of proteins and sugars, that makes up the bulk of the interstitial space. And the proteoglycans actually attract water and turn into this gel. So most of the fluid that we're talking about is this gel-like substance enmeshed in the proteoglycan frame, if you will. So there's not really large compartments of liquid just sloshing around everywhere. There are some small vesicles that are filled with fluid, and there are also some spaces called rivulets that might have free fluid in them. But for the most part, we're looking at a gel. And diffusion happens through this gel just the same as it would in the more kind of liquid substance in the blood. So that's not really going to be a big factor, but just in terms of what you're thinking about in your head, I wanted you to be clear on that. All right, so there are two main forces that determine how much fluid is going to come in and out of the capillaries. We're going to look at this first from the capillaries perspective, and then we're going to back up and look at it from a broader perspective. But from the perspective of the capillaries, we've got hydrostatic pressure, and this is probably the easiest one to understand. This is the pressure of the blood on the membrane of the capillary. So you can also think of this as if you blew up a balloon, the pressure of the air on the membrane of the balloon would be similar. Or if you had a garden hose and you turned it on and covered up the hose with your thumb, the pressure of the water on the hose itself would also be similar. So that's hydrostatic pressure, and when it increases, you're going to have more fluid leaving the capillary and coming into the interstitial space. Countering that, we have what we call oncotic pressure. I'm going to talk to you in a minute about why I'm calling it oncotic instead of osmotic. And oncotic pressure is essentially pulling fluid back into the capillaries, or at least preventing the fluid from leaving the capillaries. And basically what's happening here is that most of what we have in the blood can leave through the quote-unquote leaky capillaries. However, there are some things that are too big to get out. That would include red blood cells, white blood cells, and the larger proteins. Albumin is the main one that we have in the blood, but we also have globulins, we've got fibrinogen, and so forth. So all of those bigger proteins are going to stay in the blood despite that hydrostatic pressure. And because they stay there, there is some pull to draw water back into the capillary, or at least prevent it from leaving. And so that's what we call oncotic pressure. Now, why am I calling it oncotic instead of osmotic like it says right here? Well, it turns out that there's a specific definition for osmotic pressure that I want you to understand. So as a refresher, when we talk about osmosis, we're talking about the movement of a solution, right, towards an area of higher concentration of solute. So when we take this vessel here, we put a semi-permeable membrane in the bottom of it and fill it up with water on both sides. And we dump some sugar in one side. The sugar can't cross over the membrane. And so what's going to happen is the water is going, because of osmosis, is going to come towards the side where the sugar has been dumped. However, it won't just keep going. All of the water won't wind up across the membrane because there's a certain force that pushes back. There's a certain point where no more water is going to cross that membrane, and you're going to reach a new equilibrium, if you will. And so the force that keeps the water from coming over is basically anti-osmosis, or countering the osmotic force. That force is called osmotic pressure. All right, so when we're looking at this from the perspective of the capillary, osmotic pressure in general is anything that's countering the osmotic movement out of the capillary. So that includes the colloid pressure or the oncotic pressure, but there are other things that can also draw that water back in or keep it from leaving. So that's why osmotic pressure is kind of a broader term, and the specific part of it that's related to the proteins staying in the capillaries is called oncotic pressure or colloid osmotic pressure. Just to hopefully that's probably clear as mud, but I just wanted to throw that in there because sometimes that is a little bit of a hang up for people. As another side note, it's called colloid pressure, but um, interestingly, these proteins are not actually, the solution is not actually a colloid solution, it's a molecular solution, but it seems colloidal, so that's why they call it that. Anyway, just to further confuse people. All right, so the next thing I want to do is look at a bigger picture because we don't just have the capillaries here. There are also pressures associated with the interstitial fluid. So I want to talk to you about those. So for example, this hydrostatic pressure, this is called the capillary hydrostatic pressure. Oops, let me go back here. So there's also hydrostatic pressure coming from the interstitial fluid going the other way, so coming this direction. And similarly, there's also osmotic pressure being drawing fluid the opposite way. And all four of these different pressure gradients are going to affect how much fluid is coming out of the capillary and at what point. So I want to walk you through that here, just so you can kind of get a feel for what's happening at what point in the capillary. Now, if you recall, this up here is going to be the arterial side. So there's going to be arterioles up here. The blood comes this direction, and then it's going to exit into a venule and carry on. It's going to be moved back towards the heart. So the pressure is going to be higher. The blood pressure is going to be higher up on this end, right? Because it's closer to the heart and that pumping action. So what that means is that on this end of the capillary, you're going to have more hydrostatic pressure and more filtration, so more movement out of the capillaries. However, by the time you get down here, the pressure, the hydrostatic pressure is lower, so you're going to have less pressure moving out. The osmotic pressure in the capillaries is going to stay basically the same, theoretically speaking, the whole time. So the proteins will stay here and they'll continue to draw water towards them throughout. So that doesn't change. On the interstitial side, what we have is the hydrostatic pressure of the interstitial fluid is normally right around 0. It's normally not a big factor. However, the reason that it stays around 0 is because we have lymphatic vessels up here. So anytime the pressure of the interstitial compartment increases, fluid and proteins and whatever else are going to be carried away via the lymphatic vessels. So the lymphatic vessels are basically what keeps that pressure normalized. So if there's some kind of backup in the lymphatic system, it's not working properly, or if for some reason this interstitial compartment, the pressure increases dramatically to the point where the lymphatic system can't take care of it, then you may have some hydrostatic pressure going the opposite direction. As a side note, some areas of the body don't deal well with increased pressure. So for example, the brain, you have the skull around the brain. So if there's increased pressure, in hydrostatic pressure in the interstitial fluid, it can actually start to damage the cells out here because there's nowhere else for it to go. You don't have a lot of room for expansion. Whereas, of course, in, for example, the legs, if you have increased interstitial fluid or interstitial pressure, then your legs just get puffier, as anybody who's been pregnant in the summer might know. Okay. So we also have oncotic pressure in the interstitial fluid, which is basically related to the amount of proteins here. Again, this is not going to be a huge factor, and it doesn't tend to change as the blood flow goes from one end of the capillary to the other. So basically, what the main thing that's changing from one side to the other is this hydrostatic pressure. So on this end, what you have is more fluid coming into the interstitial space. And then down here, as the hydrostatic pressure of the capillary decreases, the osmotic pressure stays the same, and you're actually going to have more fluid being drawn back into the capillary. So basically, you reabsorb most of what gets secreted into the or filtered into the interstitial space. There's a small percentage of the fluid that doesn't get reabsorbed, and that does get taken up by the lymphatic vessels and moved away. There's one small caveat that I want to mention to you, which is that you always hear people say, oh, proteins, they don't leave the capillaries. Well, it's not entirely true. There's always going to be some proteins that do leave the capillaries, and certain types of capillaries are a little bit leakier than others, and so the more leaky they are, the more proteins are going to come out into the interstitial fluid. And of course, that is going to have some small effect on these different forces, the different pressures in the interstitial fluid and the blood flow. Now, this is another great reason to have lymphatic vessels, because the proteins, once they come out of the blood, are usually too big to come back into the capillary. And so the only way they can get removed is, again, via the lymphatic vessels, which will take them away. But depending on how long that takes, that can cause more fluid to come out of the capillaries, because you're going to increase the osmotic pressure of the interstitial space. And it's also going to decrease the osmotic pressure slightly, not a lot, but slightly decrease the osmotic pressure of the capillaries as well. So just to show you what I'm talking about here, these are three different types of capillaries, and clearly this sinusoid capillary is going to have a lot more protein loss as you move from the arterial end to the venous end than this type of capillary over here. And then lastly, I just wanted to give you a visual of the lymph. So you can see that the lymphatic vessels are closely intertwined with the capillaries, specifically so they can take away extra fluid and proteins to maintain that balance there. All right, so I hope that helps. Let me know if you have any questions, and I'll see you soon.